Okay, so for the final lectures, we're going to be discussing the theory of the Fourier transform, which is like a version of Fourier series, but for the whole real line, and also discussing how to apply these techniques to solve a variety of partial differential equations. And so what's kind of the, so for this lecture, we're going to mainly discuss some of the basic properties and theory of the Fourier transform, and then at the end of this lecture, and then in the following lecture, we'll talk about a variety of ways to use the Fourier transform to solve different partial differential equations. And so what's kind of the motivation for kind of arriving at the definition of the Fourier transform? Well, let's suppose that we're on a finite interval, say between minus L and L, and we have some function f of x. Well, let's write down its complex Fourier series. So sum from minus infinity to infinity of Cn e to the I n pi over L x, right? And so if we substitute in the definition we have for the Fourier coefficient, this ends up being the sum from minus infinity to infinity of 1 over 2L integral minus L to L f of y e to the minus I n pi over Ly, and then times the other complex exponential. Okay. And so the idea is, well, what happens if we take the limit as L goes to infinity and try to understand what happens on the whole real line, right? Because the idea is, well, this is some finite region. Let's suppose we wanted to extend this theory not just to a finite region, but to the whole real line. One natural way to do that is to write down this definition and then take the limit as L goes to infinity. And so in order to understand what's going on here, I'm going to rewrite this formula we have slightly. And so if I rearrange this, we end up with, well, our function f of x is given by, well, we have sum from n equals minus infinity to infinity, integral from minus L to L, f of y e to the minus I n pi over L y dy, e to the I n pi over L x. Oh, sorry, there should have been an x up here as well. And then we're left with 1 over 2L. And so what I'm going to do is replace this. We'll see why I'm doing this in a second. I'm going to replace the 1 over 2L by pi over L, which I can do at the expense of dividing by 2 pi out front to normalize. Right, and so now the idea is to look at, well, let's look at these terms here. Right, so when we're letting L go to infinity, what's happening? Well, the bounds of the integral are going to go to minus infinity and positive infinity, at least as long as the function f is sufficiently nice, which we'll just assume that it is. And so it's relatively easy to understand what's going on with these bounds as we let L go to infinity. And so the question is, well, how do we understand these other terms here which depend on L, and also this final term here at the end? Well, what I'm going to do is introduce a new variable to replace these. And so I'm going to use the Greek letter xi, written xi, and notationally it's like a vertical zigzag, which is pointing downwards. And I'm going to define xi sub L to the n to be this number here, to be n pi over L, right? So I'm taking this quantity here, which is changing as we let L go to infinity, and I'm just writing it compactly as this c variable. Well, notice that, I mean, these terms here aren't the only thing that depend on L, right? We also have this pi over L term here, but notice that pi over L is given by Cn plus 1 minus Cn, right? Because Cn plus 1 is n plus 1 pi over L, and Cn is n pi over L. And so their difference is just pi over L, right? And so if we have, let's say I have my number line here, let's say this is like pi over L, 2 pi over L, 3 pi over L, and so on. Well, pi over L is just the width between these different points as I let n vary, right? So this is like C1 L, this is C2 L, C3 L, and the width is given by, at each stage, by pi over L. And so I'm going to define this to be, say, the change in xi, so I'll call this, say, delta xi NL, right? But just by notational definition. Right, and so delta and delta xi NL is just pi over L, right? It actually doesn't depend on n, but you'll see why I'm using this notation in a second. And so I just want to caution, this is not the Laplacian, this just means like the change, right? So this is just this difference here as the definition, right? And so if I plug this in, what do we end up with? Well, I'm just going to replace this term and this term by the xi, and then I'm going to replace this by the change in xi, right? So I have f of x is given by 1 over 2 pi times the sum from minus infinity to infinity. I have my integral here, which came from the Fourier coefficient, right? So I'm replacing this by e to the minus I now xi. And then I have e to the I xi, which depends on n and L also, but I'm not going to keep saying it because it'll make it sound a little bit more confusing than it has to be. And then finally, we have this final term, which is the change in xi, right? And so, well, let me relabel this function here that we have in brackets, which came from the Fourier coefficient. Well, technically, the bounds here for the integral depend on L. What we're going to do is just pretend that these bounds are replaced by minus infinity and infinity, which is a reasonable change to make because we're letting L go to infinity, right? And so this argument is not completely rigorous, but what I'm trying to do is trying to motivate a formula which we're going to be using for the rest of the lecture and for the rest of the class, actually, pretty frequently. And so let's just assume that these bounds happen to be minus infinity to infinity, right? Maybe the function f is supported, is 0 outside of a big enough interval, and so eventually we'll just hit the point where this is just equal to the integral from minus infinity to infinity, or maybe the function f decays fast enough that this is a valid assumption to make. And so I'm just going to replace this by minus infinity and positive infinity. Oh, sorry, there was a y here, right? Yes. Okay, sorry. And there was an x here. Right, and so this function that I've underlined in blue, I'm going to call this not f, but I'm going to put a hat over f, and I'm going to call this f hat of this variable xi and L. Right, and so what I have here then is I've written my function f of x as 1 over 2 pi times the sum from n equals minus infinity to infinity of this f hat function of xi, which also depends on n and L, times e to the I xi x, and then times the change in xi. Right. Well, here I have a function of the variable xi, and here I have just the change in this parameter, and I'm summing up values of this function at each discrete point and multiplying it by the change. Right, so if we come back to this picture here, I'm looking at values of the function at this point, at this point, at this point, and so on, times the net change, and I'm summing these all up. Right. Well, as I let L go to infinity, this quantity here is going to 0, right? And I'm looking at a finer and finer partition of the real line. And so what I'm getting here is just a Riemann sum, right? So this is a Riemann sum, which is going to converge to an integral, right? And so in particular, as I let L go to infinity, this Riemann sum will converge to 1 over 2 pi times the integral from minus infinity to infinity of this function f hat of xi times e to the I cx dc. Right, so right, this quantity here converges to the dc, right? When you're it doesn't actually converge to dc, right? Dc is just notation, but as we let L go to infinity, this infinite sum is a Riemann sum, which will converge to a Riemann integral, assuming this function f hat is sufficiently nice. Again, we're not going to worry too much about the actual technical assumptions you need for this to be rigorously true. We're just trying to indicate where this formula comes from. Right, and so assuming everything here is valid, then we would guess that this should be equal to f of x, right? Where f hat is given by the formula from before, right? So it's given by integral from minus infinity to infinity of f of y e to the minus iy c dy, right? And so this quantity here is what's called the Fourier transform of the function f, right? So this is the Fourier transform. And this formula here that we just derived shows that you should be able to write your function in terms of its Fourier transform by using this integral formula, right? So we're going to see that by using these types of ideas, we're going to be able to, we'll switch over to the Fourier transform. It'll turn out that this makes a lot of partial differential equations easier to analyze from the perspective of the Fourier transform, and we'll be able to use this to solve partial differential equations. Right. Okay, and so let's write down the rigorous definitions. Right, so definition. Right, so f hat of c, which is given by the integral formula from above, integral minus infinity to infinity, f of y e to the minus iy c dy is the Fourier transform of f. Right, and so note that this is a function of the variable c. And c is just any real number, right? Right. Now, from what we discussed above, we expect the following theorem to be true. So we're not going to actually prove that this rigorously prove that this theorem is valid, but we at least gave an intuitive justification about how you can represent your function in terms of its Fourier transform. And so it turns out that, right, given a function f with suitable hypotheses on the function, you can always write your function as an integral involving its Fourier transform. Right, so the theorem, which is usually called the Fourier inversion theorem, or formula, right, says that, let's say I have a function f of x, which is suitably nice. For example, it has to, maybe the function decays at a fast enough rate as you go towards positive or minus infinity, and the function has sufficiently many derivatives. Then I can write my function as 1 over 2 pi times the integral from minus infinity to infinity of its Fourier transform f of c times e to the I xc dc. Right, and so this is kind of like the analog of representing a function on a finite interval as a Fourier series. But instead of as a Fourier series, it's now an integral of different values of the Fourier transform, right? Because we have this is now a function of a continuous parameter c, and so we're looking at values across the whole real line. One thing to point out is, well, assuming this formula is valid, this says that I can write my function f as a superposition of different waves oscillating at different frequencies, right? So let's say we fix the variable x. So this e to the ixc term is like a wave at frequency c, right? And so the Fourier transform sort of measures how much of the function lives at frequencies c. Again, I'm being a little bit informal here. If we wanted to make this more rigorous, I would need to spend, like several weeks developing the theory of the Fourier transform, which we're not going to do. But it's at least helpful to at least have an indication of this perspective, right? So the Fourier transform measures how much of f lives. Again, this is non-rigorous at frequency c, right? And so so typically the variable c are usually referred to as the frequencies, right? And so the Fourier transform is kind of like a function of different frequencies, right? And then the variable x is usually referred to as like the spatial variable. Right. Okay, one thing that's worth pointing out before, what we're going to do now is develop some of the properties and some of the theory of the Fourier transform, and then talk about how to use this to solve partial differential equations. But before we do that, I did want to mention one observation that's a kind of a direct consequence of this formula. So let's suppose what happens if we take the Fourier transform twice? Right, so if we begin with this function f is just some function on the real number line, which is suitably nice. Well, we take the Fourier transform, we get a new function on the real line. It's a function of technically a different variable, and it's technically a different function, but it's still a function on the real line. So let's suppose we try to take the Fourier transform again, right? So let G, actually, let me not do that, or it will confuse things more. So let's take the Fourier transform a second time, right? So I have my Fourier transform of f, and let's now do the Fourier transform operation again. So I'm going to take another hat and look at this as a function of some other variable. Say, let's look at it as a function of y. Well, if I use the definition for taking the Fourier transform, we put the function f hat, and we're integrating with respect to the domain of the function from -infinity to infinity. And then I have this exponential term, e to the minus I xc, right? Or sorry, now we have y, not x, so yxc. But if we come back to the Fourier inversion formula, this looks a lot like what I have here, right? Except the 1 over 2 pi is missing, and I have a minus sign instead of a plus sign. So by the Fourier inversion formula, let's just apply it. This is equal to 2 pi, which we need to make up for the fact that this isn't here. And then times f of y, but not f of y because we have a minus sign here, so it's going to be f of minus y, right? And so what this says is that up to flipping the sign of the input here, which is kind of harmless, if we take the Fourier transform twice, we get back to the original function up to this factor of 2 pi and this minus sign, which again, for the sake of, I mean, we can always we can always easily deal with these minor changes. We're interested in solving partial differential equations, so these things are kind of inconsequential. You just have to modify your formula slightly. So this basically says you can go back and forth between your function and its Fourier transform without losing any information, right? And so it's going to turn out that for solving different equations, partial differential equations, it's helpful to transfer things over to the world of the Fourier transform. The partial differential equation will simplify to an ordinary differential equation, and then it's easy to solve, and then you can transfer back to your original function. And so these are the types of things that we'll be studying later today and in the next lecture. But before we get into that, we do have to spend some time looking over some basic properties of the Fourier transform, which we'll be using. Right, and so what is the common notation? just to review this again, well, normally we'll have some function f, which is on the real line, where x is between minus infinity and infinity. And then we'll have the Fourier transform of f, which is denoted by f with a hat. And usually this function, which is also a function on the real line, is denoted as a function of the variable xi. And by taking Fourier transforms, again, you can go back and forth between these, as we just saw. Right, and so what I'm going to do is, I'm going to put a chart which will capture several of the important properties of the Fourier transform. So on the left part of the chart, I'll just write a particular function. And then on the right part of the chart, I'll write what its Fourier transform is. So these aren't going to be for specific functions. They're going to be for like we're going to apply some operation to f and see what happens to the transform, right? And so let me just begin with like, say, property 0. So here is f, and f hat is the transform, right? So we haven't really done anything. This is just the definition. Okay, so property 1, let's say we take our function f and we multiply it by some complex exponential, say e to the I hx. Well, now if I take the Fourier transform of this whole function, we end up with f hat of xi minus h, right? Okay, and I mean, so this should not be obvious, right? It's something we have to prove, but I'm just going to write out these properties and then I'll prove some of them. Right, and so the second property is, well, instead of multiplying f by a complex exponential, let's say I look at f and I shift x by some particular value, say f of x plus h. Well, then we get the opposite. Well, so notice that here, if I multiplied by a complex exponential and then took the Fourier transform, it changed the transform by translating, right? So multiplying by complex exponential becomes translation in the Fourier side, right? If you reverse this and you instead translate your function in x and then take the Fourier transform, well, it's kind of like the opposite. You end up with e to the I h xi times f hat of xi, right? Right, so this is kind of like in the space world, and this is like in the frequency world. Right. Right. Okay, and so this operation of multiplying by a complex exponential has a name. This is called modulation. Right, so whenever you modulate a function, it means multiply it by some complex exponential of length 1, right? Complex absolute value 1. So this is kind of like the modulation property of the Fourier transform. And then property 2, well, this is the translation property. Right, so this says that if you modulate your function, this corresponds to translating it in the frequency world. On the other hand, if you translate your function, this corresponds to modulating it in the frequency world, right? So Fourier transform switches these two, right? Right. Okay, and so the third property is related to scaling. So let's say I take my function f and I multiply its input, or I scale its input by h, where h is some number that's bigger than 0. What happens if I take the Fourier transform of f of hx? Well, I end up with 1 over h times the Fourier transform of f at xi divided by h. Okay. And so this is what happens to the Fourier transform when you scale it. And then the next two properties have to do with taking derivatives, which are going to be especially important for us because we're interested in various differential equations. So let's say instead of the function f, I look at the derivative f prime of x. Well, it turns out that if you take the derivative and then take the Fourier transform, on the frequency side, there's no more derivatives, which is why Fourier transforms end up being so powerful. Instead, you get I xi times f hat of xi, right? And so again, I'm beginning with the derivative of my function with respect to x. If I take the Fourier transform of f prime of x, I don't get the derivative of the Fourier transform, I just get a multiple of the Fourier transform of f, right? So the derivative becomes just multiplication by a polynomial. And similarly, I can reverse this. So let's say I multiply my function f of x by x, the variable x. Well, if I take the Fourier transform of x times f of x, I end up with I times the derivative with respect to c of f hat, right? And so what these two properties show is that the Fourier transform turns derivatives into multiplication by polynomials. Which is a very powerful and useful property. Right, derivatives are often hard to work with, but this just says I can, if I'm willing to work with the Fourier transform, I can replace the derivatives by just a polynomial multiple of my function and eliminate one of the derivatives. Right? Okay, and so what I'll do is prove some of these. I'm not going to prove all of them. So let's say I'll begin by proving. Let's say I'll begin by proving point 1, right? So let's go into the proofs. Right, so let's prove property 1. And so this involves the Fourier transform of e to the I hx, right? So I want to show that if I take the Fourier transform of this function, I end up with this quantity here. Well, by definition, the Fourier transform of e to the I hx times f is given by, well, let me just write this out. Well, it's the integral from -infinity to infinity, and then I plug in the function. So I plug in e to the I hx f of x times e to the minus I x c dx. Right, you're always integrating with respect to the variable of the function you plug in, and then there's the other variable up here. Right, well, let me just simplify this. Now this is the integral from -infinity to infinity. I have f of x, but I can combine these complex exponentials. So I end up with e to the minus I, well, the x variable is common, and then I have c minus h dx. But by definition, this is just the Fourier transform of f evaluated at a different point. Like c is just shifted by h. So this is just the Fourier transform of f at x c minus h. Right, and so that's exactly what we claimed up here. Right? And so the proofs of point 2 and 3 are also very similar. They're just kind of different change of variables. Right? So maybe it would be a good exercise to pause the lecture and not the next time you watch this, but pause it now and just check 2 and 3. It's really just going to be change of variables and the definition of the Fourier transform. Right. And so what's a little more interesting is the proof of point 4, property 4, which we're going to go to now, which is probably the most important of these properties, which says that, again, you can use the Fourier transform to replace derivatives by polynomial multiplication. So let's now prove property 4. Right. And so this involves the Fourier transform of the derivative of f. Right. And so, well, I guess there is a technical assumption that we need in order for this to work. So we're assuming, in fact, for the rest of the course, we're going to assume that our function converges to 0 as x goes to plus or minus infinity. If this doesn't happen, the integrals that define the Fourier transform don't make sense. So you really need this integral, or so you really need this assumption in order for everything to be technically valid. And so we're going to assume this, and you'll see where we use this assumption momentarily. Right, and so what is the Fourier transform of f prime? Well, this is given by the integral from -infinity to infinity. We have f prime of x, and then we have e to the minus I x c dxc, right? And so what this says is that we can relate this to the Fourier transform of the original function. Well, how are we going to do that? Well, remember in the definition of f hat of c, there's just f of x, there's not f prime. Over here we have f prime. But remember, if you have an integral of two functions and you want one of them involving a derivative and you want to move the derivative over from one to the other, you can always do that by using integration by parts, right? So this is what we're going to do now. Right? And so if I integrate by parts, well, what are the functions that I'm working with? Well, I'm going to let f prime be dv. I'll let the complex exponential be u. And so this means that v is given by f and du is given by, oh, sorry, this should be with respect to x up here. Sorry about that. Right, and so du is going to be, well, taking the derivative with respect to x, so this is minus ix e to the ixc, right? Because we're taking, again, the derivative with respect to x. Okay, and so if we apply the integration by parts formula, well, we end up with, this is equal to uv, which is e to the minus ixc f of x, when x is ranging from minus infinity to infinity, minus the integral from minus infinity to infinity of v, which is f of x, times du, okay, times minus ixc e to the ixc dx. Well, this is going to vanish because at plus or minus infinity, the function f is 0. Right? Which is the assumption that I mentioned a few minutes ago. So this whole thing is 0. And so we end up with just the second integral here, which ends up being, well, the minus signs will cancel. I can take out notice I can take out c because I'm integrating with respect to x. So this variable c is constant, doesn't depend on x. It's not constant, but it's independent of x. Right, so this is equal to ixc times integral from minus infinity to infinity of f of x. Oh, sorry, there should have been a minus here too. E to the minus ixc dx. But this integral here is just the Fourier transform of f, right? So this is equal to ixc times f hat of c, and so that's the proof. Right. So that's the proof of point 4. We'll see why this is so useful in later on today in the lecture and in the next lecture as well. The proof of 5, I'm going to skip this. It's very similar, right? So it's another integration by parts integration by parts type argument. If you want to see me work through the proof of this, I can do it in one of our meetings, for example, or you can ask me in office hours. Right? It's a very similar argument. Okay, and so let's look at an example and let's actually calculate a particular Fourier transform. So unfortunately, as we've seen in a lot of different problems we've worked with, it's typically very hard to, if you just pick a random function, actually calculating the Fourier transform can be very difficult. However, there are certain functions for which it's easier to calculate Fourier transforms, and so this example will be one of those. And so this involves the Fourier transform of a Gaussian. And so remember, the Gaussian was the source function when we were studying the diffusion equation. And so it's a somewhat surprising fact that if you take the Fourier transform of a Gaussian, you get another Gaussian, possibly with some different constants floating around. Right, and so in particular, let's suppose that I let g of x equal e to the minus x squared over 2, right? Then the Fourier transform of g is given by some constant, square root of 2 pi, times another Gaussian, times e to the minus c squared over 2, right? Okay, and so let's prove this. Right, well, what is the definition of the Fourier transform, or G hat of Xi? This is given by the integral from minus infinity to infinity of e to the minus x squared over 2 times e to the minus ix c dx, or dx, excuse me. Right, and so one thing to point out is that what happens if I look at G hat of 0? Well, then the complex exponential vanishes, and I just have the integral from minus infinity to infinity of e to the minus x squared over 2 dx. But we actually calculated this integral a while ago when we were studying the diffusion equation, right? This was relevant for the analysis of the source function that we had for those formulas. And so this ended up being square root of 2 pi. And we'll see that this is where this square root of 2 pi is going to come from in a minute. Right, and so returning to this integral here, there are a few different ways of calculating this. One approach is to use like the theory of complex numbers to evaluate this integral, which is what's in the textbook. Since some people may not be familiar with these methods, what I'm going to do instead is use a trick which involves relating this to a certain ordinary differential equation. And we're gonna in particular show that this function as a function of Xi solves a certain differential equation, and then the only solution has to be this complex, or this Gaussian, and then that's how we'll do this, right? And so the idea is, well, observe that what happens if I take the derivative with respect to Xi of G hat, right? This is kind of a common technique in studying differential equations. I want to show that this function here, which I have as an integral formula, is equal to this closed form function, which is not an integral, it's just like an explicit exponential. One way to show that these things are equal is to show that they solve the same differential equation, which is the approach that we're going to take. Right, so let's say I look at the derivative of G hat with respect to Xi. I'm going to bring the derivative inside the integral, which I'm allowed to do because this function decays very quickly. So I end up with integral from minus infinity to infinity, e to the minus x squared over 2, and then I have the derivative with respect to Xi of e to the minus ix Xi dx, right? Well, if I take this derivative, I end up with now integral from minus infinity to infinity of, well, the derivative of this is just ix times itself, minus ix times itself. So I get minus I, and then I have x e to the minus x squared over 2, e to the minus ix Xi dx, right? Well, notice that this term here, I have x times e to the minus x squared over 2. This is just the derivative of the Gaussian with respect to x, right? So this is equal to, right? So x e to the minus x squared over 2 is equal to the derivative of e to the minus x squared over 2 just by the chain rule, or sorry, minus, there should be a minus sign here, right? And so if I include this minus sign here, I can replace what I have underlined by integral from minus infinity to infinity. I have this I term, which is floating on the outside, and then I have derivative with respect to x of the Gaussian times this complex exponential, right? And so finally, what I'm going to do is now use integration by parts to move the derivative over. As we did in the previous example, right? As we did up here, I have a derivative, and then I have the complex exponential. Well, I can move this derivative over at the expense of adding Xi. And so just using the same argument we saw above, I end up with, this is equal to minus Xi times integral from minus infinity to infinity, e to the minus x squared over 2, and then e to the minus I x Xi dx, right? And so if you can't immediately see how I got from this formula to this formula, that's fine. What you should do is pause the lecture and try to do this calculation. It's just integration by parts, as we saw in the last example, so you should be able to do it. And if you get stuck with the integration by parts, just look at the proof that we did before this example, and you should see how to do this. Okay, but this is just negative c times the Fourier transform again, right? So this is minus c times g hat of c, right? Because this is just my Gaussian, and this integral is just the Fourier transform of the Gaussian. And so this says that the Fourier transform of the Gaussian obeys the following differential equation. Let me write it like this. So if I look at g hat prime, this is equal to minus c times g hat of c, right? Okay, but now we can just solve this using some standard techniques. So this says, for example, that g hat prime over g hat is equal to minus c. And so this says that, well, if I look at the natural log of the absolute value of g hat, if I take antiderivatives here, this is equal to e to the minus c squared over 2. Or sorry, excuse me, just minus c squared over 2. Taking antiderivatives, and now if I take exponentials, I write plus c. And if I take exponentials, this tells me that absolute value of g hat has to equal some number a times e to the minus c squared over 2. Well, I can choose this constant a such that I can eliminate the absolute values. Okay, well maybe I can't do that, but let's just pretend we're only looking at the region where, I mean, there's a minor technical issue you have to worry about here. Maybe we don't know right now that maybe g hat could be negative for some values, in which case the natural log doesn't make sense. If this is the case, you can solve this equation in another way without using taking the antiderivative of this fraction. Instead, you can use some of the first order differential equation methods, which you learned previously, to get the same solution, right? So let's just assume we know it's not negative. Well, in this case, we end up with the following solution. Well, we don't know what the constant a is immediately. In order to find this a, you need some initial condition, right? Well, we have our initial condition right up here, right? When c is equal to 0, this has to equal root 2 pi, right? Right, so we know that square root of 2 pi is equal to g hat of 0. And so if I plug in 0 to the right-hand side above, I get that's equal to a. And so a is equal to the square root of 2 pi, and therefore we end up with what we were trying to show. G hat of c is equal to square root of 2 pi e to the minus c squared over 2. Right, so the Fourier transform of a Gaussian is another Gaussian. It's a very important fact. Okay, and so I do want to at least mention one very important theorem, which we're not going to prove. And so this is the Plantarelle Theorem. And so this is exactly the analog of the Parseval theorem from Fourier series. And in particular, this relates a version of the L2 norm of the function to the L2 norm of its Fourier series. And in particular, if I look at the integral from minus infinity to infinity of absolute value of f of x squared dx, this is equal to 1 over 2 pi times the integral of the Fourier transform squared. Right, and so for example, if I know the Fourier transform and this integral is easy to calculate, well then this integral is equal to 2 pi times this integral, right? And so typically one way in which this is used is, well, maybe you know the function and you know its Fourier transform. Maybe the integral of the Fourier transform is a lot easier to calculate than the integral of the function squared. And so you can evaluate either of these integrals by evaluating the other and then using this theorem, right? And so there's also another version of this, which is more, right? So this is kind of like the L2 norm version of the theorem. There's another version which is related to inner products. And so if I look at a certain inner product of two functions, say f of x times the conjugate of some other function g of x, well, this is equal to 1 over 2 pi times the same thing, but replaced with Fourier transforms. And so again, this is usually useful for similar reasons. Like maybe these functions are hard to work with, but maybe their Fourier transforms are easier, so I can transfer back and forth by using this result. One thing to point out is that this is a complex absolute value. Right, because it's possible that the Fourier transform outputs complex numbers, right? It's not always going to be real valued. I mean, we just saw an example where it's real valued, but it may not be. If you look at the definition, you can see that it could be complex values, right? So you have to make sure you're using complex numbers, and that's one of the reasons why there's a conjugate here, right? Because we're assuming that this could be complex valued. Okay, and so maybe one quick example elaborating on what I said about how one might use this, and then we'll shift focus to talk about partial differential equations. So as an example, let's suppose that f of x is equal to, say, 1 if x is between minus a and a, where a is just some number, and 0 otherwise, where a is just some number that's bigger than 0. Well, we can calculate the Fourier transform of f relatively easily. So this is equal to the integral of f minus infinity to infinity e to the minus ixc dx, using the definition. But this is equal to 1 between minus a and 0 otherwise. And so this is just equal to integral from minus a to a. And on this region, I replace f by 1. And so I'm just left with the complex exponential here. Right. But now I can just evaluate this. It's just an integral of an exponential. So this ends up being, excuse me. Well, you have to take the antiderivative. So you end up with 1 over ixc times e to the ixc minus e to the minus ixc, right? But now I can write this as, remember we have the formula for sine in terms of complex exponentials. And so I can rewrite this now as twice the sine of axc divided by xc, right? And so this here is the Fourier transform of the function that we just started with. And so, well, now let's apply the Plantarelle theorem. So let's say I look at the integral of f hat of c squared from minus infinity to infinity. This is the integral from minus infinity to infinity. Well, I have 2 squared, which I'll replace by 4, and then I have sine squared of axc divided by xc squared dxc, right? So if I just gave you this integral here, you would probably have no idea how to calculate it, and that would be a reasonable kind of thought to have, like, how are you supposed to evaluate this integral? But the Plantarelle theorem tells you that that this is equal to 2 pi times the integral of the original function squared, right? So by Plantarelle, this is equal, excuse me, to 2 pi times integral minus infinity to infinity of the original function f of x squared dx. But this function is easy to integrate. This f of x, it's equal to 1 between minus a and 0 otherwise. 1 squared is just 1 and 0 squared is 0. So this is equal to 2 pi times integral minus a to a of 1 dx, which is equal to 4 pi a, right? Because the integral is just the length, which is 2a, and then I'm multiplying it by 2 pi. And so if I compare these formulas, this tells me that if I look at the integral from minus infinity to infinity of sine squared axc over xc squared dxc, this is equal to pi a, right? And so this is a consequence of the Plantarelle theorem. Right, and so we're not going to prove the Plantarelle theorem. The proof is it's not too hard. Okay, so when I say it's not hard, it's a very important and deep result, but it's not hard in the sense that we can do it in the class, and if you put in effort, everyone could understand the argument. The only issue is that it would take probably about 2 lectures to develop the theory we need to prove this. and we don't have enough time. So it's better to move on and look at applications to partial differential equations, which are probably more interesting to most people in the class. If you want to see the proof of this or understand more about it, I can recommend some good sources. Or in the future, you could take a class in like Fourier analysis or real analysis or something like this, where the proof of this will probably be done in detail. Okay, and so to finish the lecture today, I want to begin discussing how we can apply this tool to solve partial differential equations. Right. And so the key point, or sort of the key fact, which I mentioned before, is, well, if I look at the derivative of a function, like say with respect to the variable x, the Fourier transform of this is IC times the Fourier transform of the original function. Well, let's say I take the second derivative then, right? Let's say I look at f prime prime of x. Well, this is the derivative of f prime, right? And so if I take the Fourier transform, I'm just taking the derivative twice. And so I'm just going to be applying this rule twice. And so this just ends up being IC squared times f hat of c, and so on, right? And so you can keep applying this. So let's say I take the kth order derivative, right? I take the derivative k times, maybe k is like 1,000. So this is the 1,000th derivative, which is very complicated to deal with. Well, if we look at the Fourier transform side, it's just going to be some polynomial multiple of the Fourier transform of the original function f. Right, so if I take the Fourier transform of the kth derivative of a function, this is equal to IC to the k times the Fourier transform of the original function, right? So there's no derivatives on the right-hand side, right? And so you can prove this just by repeatedly applying this fact here, right? We take another derivative, you end up multiplying by another polynomial, take another derivative, multiply by another IC, and so on, right? And so we're going to be able to use this to kind of dramatically simplify certain partial differential equations, and then be able to solve them. So the first example we're going to look at is connecting back to what we had been talking about before this lecture, is the Laplace equation. And so let's suppose we want to study the Laplace equation in the upper half plane, which I'll define in a second. Right, so we're going to be looking at Laplace's equation, Laplacian of u is equal to 0. So our domain is going to be the upper part of the half plane in x and y. And so the domain D is the set of points xy with y bigger than 0. Right, so it's everything above the x-axis. Right, and so what I want to do is consider the following boundary value problem. Right, I want to find a function u of xy such that Laplacian of u as a function of x and y is equal to 0 in the upper half plane, with the following boundary condition. So when y is equal to 0, u is equal to f of x, right? So in this region, Laplace u is equal to 0, and on this axis, u is equal to some given function. Excuse me, u is equal to some given function f of x. Okay. Okay, so if we think back to earlier in the course, we would maybe try to do this using separation of variables, but the problem is, for the separation of variables method to work, we really needed a finite domain for x, but here we have an infinite domain for x, and so separation of variables may not go through. Instead, we're going to use a different technique, which is the technique of the Fourier transform. And so let's do this now. Well, what happens to, like, what is the equation that we're trying to solve, right? So we want well, I want second derivative with respect to x of u plus the second derivative with respect to y of u. This is the Laplacian. I want this equal to 0 when y is bigger than 0. Right. What I'm going to do is take the Fourier transform in the x variable. Right. So I'm going to fix y and take Fourier transform in the x variable. Right. And then we're going to see what happens. The reason why we're doing this is, well, this derivative here is going to change to a polynomial. And so we're only going to have one derivative to worry about, and then we're going to end up with an ordinary differential equation, which we can solve. So let's do the details now. To simplify this a little bit so that the notation doesn't get too confusing, let me rewrite this as u. I'm going to put the y in the superscript x, right? And so this will be, I'll replace this by uy x. And so now fixing y and viewing this as just a function of x, I'm going to take the Fourier transform, right? And so we end up with, well, I have the second derivative with respect to x of u, and I want to take the Fourier transform of all of that, and then also take the Fourier transform of second derivative with respect to y. Right. And this is all equal to 0, right? Because, well, if you take the, I mean, we're taking the Fourier. So the left side here is equal to the right side. That's the equation we're trying to solve. And so if I take the Fourier transform of the left side, it should be equal to the Fourier transform of the right side. But the Fourier transform of 0 is just an integral of 0, which is 0, right? So if I take the Fourier transform of the left side, that should also be equal to 0. So this is what we've done. But now I'm going to use the derivative property. Right, so on the left-hand side of the equation below, we had the Fourier transform of the second derivative, but that's just equal to IXC squared times the Fourier transform of the original function, right? So this is equal to IXC squared times Fourier transform of UY XC, right? And then what am I left with? Well, I'm left with the second derivative with respect to y of Fourier transform of uy xc, and this is equal to 0. Right, so why did this derivative with respect to y not change the Fourier transform? Well, everything is as a function of x, right? And so this operation with respect to y doesn't affect the definition of the Fourier transform. Let me just carefully write out the details so you can check that, right? So this is equal to, by definition, this is integral from minus infinity to infinity of derivative with respect to y of u of squared, the second derivative with respect to y of u of xy times e to the minus I xc dx, right? Well, since y is, I mean, you're not integrating with respect to y, and here we're differentiating with respect to y, which is not the variable of integration. And so I can bring out this derivative to the outside, right? So this is equal to second derivative with respect to y, integral minus infinity to infinity, u of xy, e to the minus ixc dx. But that's exactly what we have here, right? So this is second derivative with respect to y, integral minus infinity to infinity. By definition, this is just uy of x, e to the minus ixc dx. Sorry. Right, and so that's why I can just factor out the derivative operation here. Right? If this derivative involved x, I couldn't do this, right? Because then I would be stuck because I would be looking at the Fourier transform of some derivative with respect to x. Right? Okay, but at the end of the day, right? So what's kind of the main point here? Excuse me. What's the main point here? Well, here I have derivatives with respect to the variable y, but I have no other derivatives anywhere else. So this is an ordinary differential equation, right? And in particular, just to maybe simplify things a little bit, let me call this capital U, not G, capital U of Y. And let's call this thing capital U, U of Y as well. Right? What does this say? This says that IC squared times U of Y plus the second derivative, or U prime prime of Y, is equal to 0, right? And so this is just an ordinary differential equation in the variable Y, right? And so in particular, let's just rearrange this. This says that U prime prime of Y is equal to C squared U of Y, right? And so this is the ODE that we have to solve, right? Because, well, I squared is -1, and so, right, so this is minus C squared, right? Okay, and so now we've taken a complicated partial differential equation, which is the Laplace's equation in a certain domain, and we've reduced it to just a one variable ordinary differential equation. So notice this C here is fixed, right? It doesn't depend on, fixed for now, it doesn't depend on Y. And so let's just solve this now as a function of Y. This is just a second order linear ordinary differential equation. And so the solution is given by, well, there's actually two main parts to the solution to this particular ODE. So I have some constant A times e to the minus absolute value of cy. And there's also another exponential corresponding to the opposite sign, so plus b times e to the cy, absolute value of cy. You can show relatively easily, again, using the techniques for just a first order linear differential equation, that this is the kind of the general form of the solution. The only issue is that, well, I'm assuming y is positive, right? And so a lot of things that we're working with involve integral formulas, and so this thing doesn't decay as y goes to positive infinity. So there could be some issues with some formulas if we try to include this. And so we're going to assume that b equals 0, right? And so I'm going to pretend that that's not there. And so in this case, I end up with u of y as my solution is a times e to the minus cy. Okay, well, we're not quite done, right? This is not the solution to the Laplace equation. This is just the solution to this ordinary differential equation, which we arrived at. And so now what we need to do is like unwind all the definitions and try to interpret this in terms of the original function. Right, so this u of y was really the Fourier transform of my original function u xc with y fixed, right? So I'm taking the Fourier transform with respect to x, and y is fixed at c, and we just show that this is equal to a times e to the minus absolute value of cy. Okay, and so now the next thing to do is to try to solve for a, right? And so, well, this tells me let's continue unwinding the definitions. So on the left-hand side, this was the Fourier transform of u as a function of x. Right, because this here is by definition uy of x. And so we've shown that this integral is equal to a times e to the minus e to the minus cy. Well, in order to solve for a, we need some kind of initial condition. For example, what happens if we set y equals 0, right? So now we're trying to solve for a, so let's set y equals 0. Well, then we end up with integral from minus infinity to infinity of u of x0 e to the minus ixc dx is equal to a, right? Because y becomes 0, so this exponential just becomes 1. But remember, we also had this initial condition, or this boundary condition, which is when y is equal to 0, we want u equal to f, right? And so if I come down here and plug that in, well, this is just f, of x. And so this tells me that a is equal to integral minus infinity to infinity of f of x e to the minus ix c dxc. And so therefore, well, this is just the Fourier transform of f. So a is equal to f hat of c, Fourier transform of the boundary condition. Right. And so therefore, we end up with I'm sorry. Right, coming back to this formula here for the Fourier transform of u with y fixed, right, I can plug this in for a. And so the Fourier transform in x of our solution u with y fixed is given by, at the point c, is given by f hat of c times e to the minus absolute value of cy. Right. Okay, but now we're going to apply the Fourier inversion theorem. Right. So my original function, or my solution u as a function of x and y, this is by definition uyx. This is just the notation. And so now applying the Fourier inversion theorem to this function, well, this is equal to 1 over 2 pi times integral from minus infinity to infinity of the Fourier transform as a function with respect to x, right? C dxc, right? But we've just evaluated this function here, right? So now I can plug in. Right, and so this tells me now, again, using the Fourier inversion theorem, that u of xy is given by 1 over 2 pi integral from minus infinity to infinity. Then I have Fourier transform of f, which is the boundary data, times e to the minus absolute value of cy, e to the ixc, right? And so this is my solution to the boundary value problem for the Laplace equation in the upper half plane. So I guess technically this is the Dirichlet boundary value problem, because we're not specifying information about the derivative on the boundary. We're just saying it's equal to some given function on the boundary, right? And so what this analysis shows is how you can use the Fourier transform to solve this boundary value problem. And so, as is hopefully not as surprising at this point in the semester, this is not like a very simple formula, right? In order to actually calculate this, you would have to take your boundary function, boundary data, you would have to evaluate the Fourier transform, and then you plug in that Fourier transform to this integral, and then evaluate this whole integral, and then you get your solution. And so, unfortunately, for a lot of functions, it may be hard to actually calculate these integrals, although there are a variety of numerical techniques to approximate the values of integrals like this, which for the purposes of a lot of applications are sufficient. And so especially if you're interested in like engineering or physics, maybe it may be helpful after this class to take a class in numerical methods for partial differential equations, where you'll talk about how you would actually calculate things like this without actually explicitly evaluating the integral using pen and paper, which is sometimes hard and sometimes impossible. Okay, and so I guess that's it for today. And so the next lecture we'll review what the methods that were used here, and we'll look at some more examples of how you can use the Fourier transform techniques to solve some other partial differential equations.